Je suis heureux de souhaiter Katharina Duthiel-Novaes qui va nous parler en anglais sur son livre qui vient de gagner le prix Lakatos, qui est un prix assez prestigieux donné par London School of Economics. Et elle va parler des thèmes du livre.
Oui. Merci. Excusez-moi, effectivement, je vais faire ma présentation en anglais, mais je serai très contente de discuter si vous avez des questions après la conférence, si vous voulez en discuter en français. Je ferai mon possible. Mais bon, voilà, le reste, ce sera en anglais. So this is a presentation that is indeed based on this book that I published. The book was published already almost 3 years ago, and it received the Lakatos Award last year, so it's not that recent anymore, but still, of course, still in my recent memory. And I'll focus in the book, in this presentation, I'll focus in particular on the parts of the book that pertain to mathematical practice, in particular, the way mathematicians engage in practices of proofs. So that's the topic of the, okay, it works, right? So the name of the book is The Dialogical Roots of Deduction, and in the book I offer overarching conceptualization of the notion of deduction as based on dialogical practices. So it's very overarching. It talks about also cognitive science, the history of deduction, history of mathematics, but also mathematical practice. And what I argue in the book is that mathematics, the deduction very generally, not just in mathematics, has dialogical roots. And these dialogical roots are still present both in theories and in practices of deduction, in particular in practices of mathematics. And the account as a whole, it highlights what it seeks to do is to highlight the human and social nature of mathematics, of deduction, and mathematics in particular, as embedded in these actual human practices. So rather than discussing, say, the ontological status of mathematical entities, such as sets and numbers, etc., these are not the questions that I'm interested in the book. Okay? So it's really bring it down to what people do, in a more concrete way. This is the cover of the book. It's a painting by the Dutch painter Vincent van Gogh, you may recognize. It has trees and roots in it, so I guess the connection is hopefully clear enough. And the book has 3 parts. The first part is on more philosophical topics pertaining to deduction. The second part is the more historical part, and the third part is where I engage with, let's say, the real world, and that includes mathematics education, the cognitive science of reasoning, and also in the very last chapter, mathematical practices, looking at what mathematicians really do, research mathematicians. And in this talk, I'll draw from different chapters of all 3 parts. Hopefully this will give you enough of a sense of, although I won't tell you everything either, right? I won't be telling you about the whole book, that wouldn't fit. So I selected some of the parts that I thought would be relevant for hopefully for this particular audience. So I'll start with a bit of history, right? I'll start, because that's also how I myself came to develop these thoughts. I started really reflecting on the history of logic and mathematics in ancient Greece. Then I'll present you the philosophical model that I developed in the book, and which then I use to apply to a number of open questions in the philosophy of mathematical practice. And then in the third part, that's the longer part, that's where there's going to be a bit more mathematics. That's when I look at those 2 characters from my model, provers and skeptics, how they actually are embodied by mathematicians in their practices of proof. So that's the structure of the talk. Starting with the history, right, starts where it often starts, right? So it's not a very original way of doing history of logic and philosophy, but of course we still are very much indebted to the ancient Greek philosophers. So what's really important for me here is to embed these theoretical developments, both in mathematics and philosophy and logic, in a broader political, cultural, social context.
What do you mean by dialogical?
It will become clear. So I start with this. So one sense is this sense, it's the political sense, where people in ancient Greece, in the Athenian democracy, where there was this very important role for debates, for practices of debating, right? So both in the assembly and in the courts of law. So it was very important to be a persuasive orator. This was very important as a citizen. And in the background, there's very much this polemical setup where these orators, they're making speeches that are for or against positions, because the votes by the citizens in the assembly were just yes or no votes, right? So you had to take a stance. And in particular, as it's well known, some people in particular presented themselves as those who could teach people to become good orators. And those were the sophists, right? So known now as the sophists, the rhetoricians, right? So they were the ones who taught citizens to perform well in these situations. And this is, of course, what's happening in the so-called golden period of the Athenian democracy. But of course, with the Peloponnesian Wars, there was a very steep decline in Athens as a power, as a regional power, and of democracy in general. And this is very much the time when Plato is, when he's born and when he develops intellectually. So what he experiences, Plato, is the decline of the Athenian democracy. He doesn't experience the golden age of the Athenian democracy. And this is one of the reasons why Plato is extremely critical of democracy, as you may remember from the Republic, from the Gorgias. Well, those of you at least who are interested in philosophy and the history of philosophy. But he's very critical of democracy and very critical of the sophists. Right? So people like Plato and then his mouthpiece, Socrates, they're criticizing the sophists because they think the sophists only look at persuasion and don't care about truth. Right? This is a very, broad simplification, but roughly that's how it goes. And they think that's precisely this disregard for truth is one of the causes for the demise of democracy as a political structure. Right? So this is the background. This is the political background. That's their political intellectual background. Yes. And in this background, against this background, people like Socrates and Plato and later Aristotle, they were looking for a different model of intellectual inquiry where truth will have a more important role to play than in the mode of intellectual inquiry of the sophists. And it's often said in the literature that, well, they want truth instead of persuasion. That's why they criticize the sophists. But together with other scholars of ancient Greek philosophy, we think that this is the wrong way to think about it. We should think about truth with persuasion for people like Plato and Aristotle and Socrates. And this is where you have the practice of dialectic that emerges. Right? So the dialectic are these dialogical interactions where speakers take turns in quick succession. Think of many of Plato's dialogues. Right? So this is where Socrates says, well, don't you think that this is the case? And then the student says, yes, of course, Socrates, you're right. And this, of course, is these are the less interactive parts. There are other parts that are much more interactive, but that's the idea. And in particular, in these dialogues, what you have is also the concept of elenchus, which is refutation, but translated as refutation, which is the technique where by means of questions, Socrates or somebody else, but often Socrates, will elicit discursive commitments from the interlocutors. And then show that these discursive commitments taken together are incoherent. They lead, for example, to a contradiction. Right? So this is the technique of the elenchus of refutation. And this is very much, I won't get into the details of this, but this is very much at the heart of what we now call reduction absurdum proofs. It is exactly this. There's a collection of statements which taken together are incoherent. Something has to go. Right? So that's very much, I think, the historical background, for example, for the development of reduction absurdum proofs, which were already in use then, right? In Euclid, we already see many of them. And what's important for me here is that here there's this implicit notion of implication, right? Because when you elicit discursive commitments from the interlocutors, and then you show that taken together they entail something absurd, there's some notion of entailment there that's already doing a lot of the work, right? So someone affirms P and grants Q and R, but Q and R together imply not P. So it's this sense of implication, right? That Q and R imply not P, but this person has also affirmed P. That's when you get to an incoherent situation, okay? So this is one of the ways in which the idea that deduction is dialogical is unpacked in the book. This on the side of, let's say, philosophy and logic. But at the same time, in mathematics, very similar developments were taking place, and this has been extensively studied by the historian Raviel Netz, who published this book, which is more than 20 years old, but still the most comprehensive history of the emergence of deductive reasoning in ancient Greece, called The Shaping of Deduction. And this is something that he says in the book. Greek mathematics reflects the importance of persuasion. It reflects the role of orality in the use of formulae in the structure of proofs. But this orality is regimented into a written form where vocabulary is limited. Presentations follow a relatively rigid pattern. It is at once oral and written. And this is the main slogan of my book. It is at once oral and written. Right? So mathematical proofs, I will claim, on the one hand, they have these dialogical origins where, for example, you have the very famous passage from the Meno where Socrates shows the boy how to double the area of the square. Maybe some of you remember this particular example, right? It's this dialogical thing. So Socrates says, how would you do this? And the student says, well, what if I double, right, the sides of the square? Oh, yes, well, then it doesn't work, because then in the end what you're doing is you're quadrupling the area instead of doubling. Oh, okay, so then, right, so this is how this kind of process, this interactive process, which you see, for example, in the Meno, my claim is that this is really kind of at essence, the origin of deductive mathematical proofs. But at the same time, they're already at this early stage, they're transformed, in particular with the use of all kinds of written devices, symbolisms, right? Then in that sense, they already are this hybrid entity, which is at once oral and written. Okay? So that's the story. So given this historical background, which I analyze, of course, in more detail in the book, what I propose in the book is this rational reconstruction of these dialogues, right? So this is the philosophical story of, like, this is a philosophical model to think about how mathematical proofs work. And this is also very much informed by work in mathematics education. And so, I mean, there are a lot of sources for this model. So the three features that I claim are the conceptual cornerstones of deduction are the property of necessary truth preservation, which is the one that I think is most readily associated with mathematical proofs. Then there is the property that I call perspicuity, which means that every step in a proof has to be sufficiently clear for its intended audience, right? It's intended to be an explanation in this sense. And what I call belief bracketing, which is the idea that when you're reasoning deductively, you don't care about the truth of the premises, right? You're just trying to tease out what you can conclude from them, even if you don't believe in them. And this may, certainly for an audience of people interested in mathematics, this may seem quite trivial, right? Yeah, of course, that's what you do, right? You reason hypothetically in mathematics. But I also draw a lot on findings from the psychology of reasoning literature, for example, which show that people find it very difficult to do this, right? To reason on the basis of premises that you don't, being indifferent with respect to the truth value of the premises. So these are the three conceptual cornerstones of the method, we could say, the method of deduction. And all of them can be interpreted dialogically, so that's the story. So here you have, for necessary truth preservation, you have this idea that the argument is going to be indefeasible. Nothing is going to, once the argument is established as having the property of necessary truth preservation, no new premise, no additional premise is going to change that, right? So that's the notion of indefeasibility. The arguments, if they're correct, they have no counterexamples. Right? There's nothing that somebody else can do to knock them down, as it were. And here there's this sense of adversariality in the background, and this is something that has already been developed by other dialogical conceptions of logic. Some of you may be familiar with the dialogical logic by Paul Lawrenson. Right? This was a tradition in logic in the 20th century, still ongoing, and especially, for example, here in France, there's a strong group working on this in Lille. There's also game theoretical semantics by Jaakko Hintikka. So these are also logical accounts of logic that draw on this idea, these dialogical ideas, but that emphasize very much the aspect of adversariality. So both these accounts, they see proofs as winning strategies for the prover. Right? So there's that story, and to some extent, I approve of this story, I endorse it, but I also very much emphasize the cooperative nature of mathematical proofs. And this is where me and these other people, we disagree, at least in terms of emphasis. I think that a mathematical proof, while it has a small component of adversariality, by and large, it's a cooperative endeavor. Right? By and large, when somebody, say Tim is producing a proof, and then there are colleagues who are helping him work through the proof, and they're looking for mistakes in the proof, what they're doing is really helping Tim rather than being adversarial, right? It's really this idea that, well, when you're working through a proof together, you're working together to make it better, right? And then, so that's I think it's a very important distinction between my story here and other previous accounts, dialogical accounts of logic and deduction. So this leads me to the development of this model with these two fictive characters, prover and skeptic. Right, so the other frameworks, for example, dialogical logic uses the terms proponent and opponent. I don't like these terms. I think it emphasizes too much the adversarial component, whereas I want to also emphasize the cooperative component. Instead, I use the term prover and skeptic, which again I didn't invent. This is also something that is developed in the literature in computer science. So we have two fictive characters. Prover is going to put forward a proof, a purported proof of a theorem, and the skeptic is the one who's receiving the proof and is trying to see if the proof is okay. Right? The other participant is a skeptic in the sense that the skeptic is not easily convinced and is going to be looking for all possible flaws in the proof. And the proof, the dialogue starts with when prover states the theorem and asks skeptic to grant certain premises. Right? So that's the story. So I say, well, here's what I want to prove. Do you grant me these and these premises so that we can get started? If skeptic grants the premises, then the prover proceeds to establish the conclusion in a stepwise way, right, with individual inferential steps. And what does skeptic do? Skeptic at the very beginning can grant or deny premises, right? Skeptic can also say, well, these premises that you're asking me are so trivial, right, taken together, that nothing interesting is going to come out of this. Sorry, let me have a sip of water. So what skeptic does is grant premises at the beginning. Skeptic can come up with counterexamples if there are problems along the way, if there are inferential steps that don't have the property of necessary truth preservation. And skeptic can also ask for further clarifications when there are steps in the proof that skeptic doesn't understand. So this is not the same as coming up with a counterexample. This is saying, wait, you're going too fast here. You need to unpack this for me a little bit more. So that's why I say there is some amount of adversariality, right? In the sense you're looking for counterexamples. Maybe you're trying to destroy the proof, as it were. But by and large, you're cooperating, right? By and large, a skeptic is helping prover to produce a proof that's correct, and that is also clear and informative. So this is a tree. It's probably too small to see, but maybe you can see like this is a tree that gives you the different steps in the game, right? So here's the beginning, when prover states the thesis and asks for premises. So if the skeptic refuses to grant this particular premises, that's it. That's the end of the dialogue. If the skeptic comes up with a counterexample, a global counterexample immediately, right? So this is a situation where the premises that prover put forward, asked a skeptic to grant, are the case, but the conclusion is not, that's a global counterexample. That's also the end of this particular dialogue. By the way, this terminology, global and local counterexample, comes from Lakatos, right? So the person who gave the name to the prize, to the award that the book got. So that's, you know, I draw quite a bit on Lakatos in the book. And then, but if all goes well, then skeptic grants the premises and the conversation, the dialogue can begin. So then there is a first inferential step, right? So prover says, oh, right, so if you've granted me these premises, then you also grant me this other conclusion, right, this preliminary lemma. And then once this happens, when an inferential step takes place, there are three options again for skeptic. Either skeptic agrees, has no objection, just kind of nods, okay, right? It's called the no move. But then there's also, and if that's the case, then the next inferential step will take place here. Or here, if skeptic thinks, I don't understand what's happening here with this step. It's going too fast for me. Skeptic says why, and then prover has to clarify. For example, prover has to break down the step into smaller inferential steps, right? Give more detail. And then again, here then we have the same thing, right? And that if then now skeptic is satisfied, then things continue. But of course, if skeptic finds a local counterexample to this particular inferential step, then prover has to withdraw this particular step or modify it, right? Or maybe introduce, because a skeptic finds a counterexample and he says, okay, so then I have to restrict the range of my claims so as to avoid this particular counterexample, okay? And this goes on, right, until, if all goes well, then P arrives at the conclusion that had been stated at the beginning, the theorem, and S says yes, and that's your proof. Now you've produced the proof together, right, prover and skeptic. But of course, things don't always go right, and I'll give you some examples of that. And it can happen that the prover simply gives up on the proof because the issues that skeptic has spotted really seem beyond repair, okay? So this is basically like where things go. And also on the side, skeptic prover can ask for additional premises along the way, right? It's not just at the very beginning you ask for premises and afterwards that's the end of it. No, it can also happen along the way. And another thing that is not in this chart, and it's something I'm very interested in, and maybe I think you had a talk on this last year, is the role of imperatives. Is this what Fenner talked about? Yeah. The role of imperatives in mathematical proofs. It's extremely, extremely interesting, and Fenner Tanswell, who is a colleague working in Berlin at the moment, has been doing very interesting work on the role of imperatives. When you say, draw a triangle A, B, and C, right? Or you say it in the passive voice, let there be a triangle B and C. But this is also an imperative. But I'm not talking about this today, but very interested also in the occurrences of these kinds of speech acts in the dialogue. So that's the theoretical background, the historical background and the theoretical background. And now I'm going to show you what I think we can do in terms of understanding mathematical practice with this model that I've been describing to you, right? Because you might say, well, what do I do with this, right? You told me this story. So what I will do now is talk about specific practices among professional research mathematicians and argue that my model illuminates a number of features of these practices in an interesting way. So, in particular, the practice of peer review is very much at the heart, is very much the real counterpart, or the counterpart in the real world of this model that I was describing. right? Prover and skeptics are embodied in peer review mathematics, peer review practices in mathematics. And this happens both formally, right, when a mathematician submits a paper to a journal and it gets sent to referees, but also, perhaps even to a great extent, informally, right? Either with your immediate colleagues, or of course because you've uploaded something on archive, and people who are interested in this get the notification, oh, there's this new paper in your area, so you go check, and then maybe you're going to go, you find it interesting, you go through the proof, and then you find mistakes, you write to the author. So this is what I would call informal peer review, which I would claim is even more important in mathematics than a formal peer review for journals. And this is just a random picture that I found on the internet of how do you read, if you're a professional research mathematician, how do you read a mathematical paper? This is what you're doing, right? You're just scribbling on the side and you're writing why where you don't understand, or question marks, all right? So you're engaging in a very active way. So this is a way in which you're being the skeptic, right? So that's why I say on the one hand, the proof is already produced, right? It's already in the paper and printed. So you might think, well, where's the dialogue here? Well, the dialogue is when somebody is going to read this paper and is going to engage with this paper in this very active way, right? Making all these annotations and asking questions, right? So that's the idea that there's this ongoing dialogue, even when it doesn't look like it's a dialogue, probably speaking. An interesting feature about mathematics is that typically, for a journal, a paper is refereed by only one expert. And in many other fields, it usually have two or even more referees. And also the process is not double anonymous. In many other fields, there's this idea that the referee should not know who the author is, and the author should not know who the referee is, so that the process is not unbiased and all this. And interestingly, in mathematics, this is not common practice. So it's interesting to look at the kind of sociology of peer review and how it changes per fields, right? So, and in mathematics, there's a fairly different structure. Papers are made available as preprints through archive, so they are very quickly available to the whole community. Right, so for those of you who are not interested in how these things go outside mathematics, maybe all I'm saying here is not particularly informative, but as a philosopher, and also many other people coming from other fields, this is quite unique. It's quite a different way to do peer review when compared to other fields. So what does the skeptic do? The skeptic doesn't only check whether the proof, from her point of view as a skeptic, if the proof is correct. No, the skeptic checks for checkability. What does this mean? It means that the referee is kind of representing the whole community, which is supposed to be the target audience of this paper, right? So when the referee checks the proof for correctness, she also takes into account whether others in the same community would be able to verify the proof, to run through the steps of the proof. Right? So she doesn't only comment, right? So going back to these comments here, if you're a referee for a journal, you're not only commenting on the parts that you cannot follow yourself, but also parts that you think will be hard for other members of the relevant community to understand, right? So you're really playing this social function of making that proof intelligible for its intended audience, right? And so the idea is that a large majority of the experts in the field, in the specialized field, should be able to validate the proof within a reasonable amount of time. So this is what you want your published proof to look like, that it can be verified by a wide majority of the relevant experts in a reasonable amount of time. And of course, this means that how detailed the proof will be will depend on the intended audience. So I'm always talking about the intended audience of a proof. So if you're writing a proof for a textbook for first-year students, of course it's going to be more detailed, right? Because you don't expect the intended audience to be able to unpack the details of the proof themselves. If you're you're writing for an audience of professional research mathematicians, then the expectation is that they'll be able to unpack the details of the proof much better themselves, right? So then the proof can be much more brief, much more, a lot of the details are left out, right? So this idea of checkability was introduced by this researcher in mathematical practice, Lina Anderson. She wrote a PhD on the practices of peer review in mathematics. She interviewed a lot of mathematicians on their research practices, right? And what she says in this paper in 2018, she says the following: contained in the published proof are the author's responses to the responses of this voice, and the voice is the referee's voice representing the subcommunity, to the author. In this sense, the proof can be said to consist in a dialogue between the relevant community and the author. This suggests that we speak of a published mathematical proof as a piece of discourse with the relevant audience, not only as a piece of discourse aimed at the audience. So it's with the audience, it's created by means of this interaction, right? Which in the case, so there's this one referee who's representing the community. But this is the idea that, and of course many times there will be more than that, right? There will be other people who engage. There will be a broader range of skeptics engaging with the proof. And when you as a prover, you need to be responsive to this. And then if people are spotting problematic aspects of your proof, well, then you better work on them and make the proof better. So this is the theory, and now I'm going to discuss 4 examples of actual events in mathematics where I think the model really sheds light on what exactly is going on there. So the first one is the reception of Gödel's incompleteness results. It's going to be 100 years in a few years from now. I'm not sure if everybody is familiar with Gödel's incompleteness results. So I just have a very kind of simplified statement of at least the first result here on the slide. So what Gödel has proved is that no consistent system of axioms whose theorems can be listed by an effective procedure, like an algorithm, is capable of proving all truths about the arithmetic of natural numbers. So the idea is that there are propositions, mathematical propositions that are true but cannot be proved, right? That our ability to discover mathematical truths by means of proofs is limited, right? And this was a big blow to so-called Hilbert's program, right? So Hilbert had this optimism that you can prove everything about mathematics from inside mathematics, right? So you could do mathematics inside mathematics, and when Gödel proved his incompleteness result, this was a big blow. It showed basically that Hilbert's program as originally formulated was not going to be realized. And this happened in September 1930. This was the first public announcement of the incompleteness results. And at the time, most mathematicians were very surprised by this idea that there are these mathematical truths that we cannot capture with proofs. Because they were still kind of coming from this Hilbertian optimistic background where they thought, we will know, right? We will know, we must know. That's the Hilbertian slogan. Maybe some of you may remember that. And so they were surprised and they thought there must be a mistake somewhere in the proof. But everybody who got to see the proof, because of course this was way before the time of the internet, so people didn't easily have access to the details of the proof. And then those who hadn't seen the details yet, they thought, no, there must be a mistake somewhere, many of them at least. But everyone who saw the details of the proof immediately became convinced that it was correct. And so here I have something that mathematician Leon Tristek, I think, sorry. Thank you. Are you Polish? Yes, apologies. So he wrote in a letter, he said the following: now that I've seen the whole proof, first he said, first I thought there must be an antinomy somewhere, right? There's some paradox going on. And then he says, now I see that this is out of the question. The method is truly wonderful and it fits pure type theory thoroughly. So what's the take-home lesson from this episode? Is that there's a very surprising result, but the proof was very well done and very clear, right? So Gödel had been a very cooperative prover and had really, produced a proof that was very clear. And that made the job of skeptics quite easy, right? A skeptic such as, I don't dare saying the name anymore. Can you say it? Tristek. he could write, he could just from reading the proof, he would immediately see that it was correct. And not only that it was a wonderful method, that it was an extremely important and insightful proof, which it is. So that's the story here. The story is that a prover proving something original, very unexpected, and yet, because the proof was so thorough and detailed, the job of skeptics, of all the community receiving it, was quite easy, as it were. Here's another case, more recent one. This is Wals's proof of Fermat's last theorem. So again, I just have a simplified statement of Fermat's last theorem here. Note 3 positive integers a, b, and c satisfy the equation a of n plus b of n is equal to c of n for an integer value of n greater than 2. And this was, of course, formulated by Fermat way back, centuries ago, and then allegedly he wrote in the margins, I have a wonderful proof of this, but I don't have the space for it. And so for centuries, people thought, what would be the easy proof, wonderful easy proof that he had? And people were working on trying to prove Fermat's last theorem. And it was only in 1992 that Andrew Wiles came with, announced that he had a proof of it. He did it with great, allure and fanfare. He was at a conference, and then, right, maybe you even were at that conference. You were, right? Yeah. And then at the end he said, and therefore I've demonstrated Fermat's last theorem. Well, big commotion in the room. But then what happened was that he, of course, still had to have that proof verified, right, by the community. So what he did is he sent the proof to a very important journal. What's the name again? I forgot. Is it the Mathematics? Yeah, well, I think it was a different one, but never mind. And then the editor of the journal split the proof in 6 parts and sent it to 6 different referees, right? Because it was a very complicated, long proof, so this had to be teamwork again. One of these referees was this mathematician called Nick Katz. And he got this big chunk of the proof. And then now comes like a description from a popular science account of these events. For 2 months, Nick Katz and a French colleague, Luc Ilusi, scrutinized every logical step in Katz's section of the proof. From time to time, they would come across a line of reasoning they couldn't follow. Katz would email Wiles, who would provide a fix. This is the skeptic, right? The skeptic saying, why? What's happening here? And then Wiles would provide the fix, right? It would unpack the steps, the step in a way that would be more perspicuous. But in late August, Wiles offered an explanation that didn't satisfy the 2 reviewers. And when Wiles took a closer look, he saw that Katz had found a crack in the mathematical scaffolding. At first, a repair seemed straightforward, but as Wiles picked at the crack, pieces of the structure began failing and falling away. So this was a fairly dramatic event. It was a very serious flaw, and it took Andrew Wiles together with Richard Taylor a whole year to fix this particular problem. So these were very diligent, good skeptics who were, on top of things and found the problem, asked the right why questions, and thereby helping Wiles to find a very serious mistake in the proof. So this is when you see there's really this cooperative process going on between the prover and, in this case, these 2 skeptics who are helping Wiles to improve his proof. Okay? Another fairly recent event, was in 2011. There was somebody called Ed Nelson, who was a mathematician in Princeton. In the meantime, he has sadly died. But he claimed in 2011 that he had a proof of the inconsistency of Peano arithmetic. So that's also it's as bombastic, if not more, I think it's even more bombastic than Gödel's incompleteness theorems. Okay? Because obviously if Peano arithmetic is inconsistent, there's so much that we have to revise about everything we know about mathematics. So Peano arithmetic, just in case people aren't familiar with the idea, Peano arithmetic is a set of axioms describing the set of natural numbers and basic arithmetic operations. Right? So it's an axiomatic system which is supposed to be an axiomatization of arithmetic. And, so then this guy said, well, this thing is inconsistent. So, wow, right? But, and he announced this on this FOM, Foundation of Mathematics mailing list. Those were the days when people still kind of, followed mailing lists, I think much less now. I used to follow this mailing list, but then I quit because it was very nasty. Did you get that experience too? I mean, people were very, it was very, there was a lot of adversarial, interaction going on. Anyway, but in the list, so he provided 2 formulations of the proof in book form and a short summary. So, but very soon, because of course now we're in the times of the internet, so these things circulate very, very fast, right? Contrary to when Gödel announced his results, because people had to actually somehow get a copy of the proof on paper. Now it's all on the internet. And 2 people independently, Terry Tao and Daniel Tausk, who's a mathematician in Brazil, they found the problem in the proof. And told Nelson about the problem, said, look, we think that there's this problem. And first Nelson said, no, I don't think it really is a problem. But very quickly, it was just a matter of days. All this is playing out in a matter of days. Nelson agreed that it was beyond repair and withdrew the proof, right? So this is, let me see if I can go back real quick. This is when this happens, right? Nelson gave up on the proof. Right? So these 2 skeptics came up with this very serious objection, and he said it's beyond repair. I don't claim anymore to have a proof of the inconsistency of Peano arithmetic. Okay? So far we've had the different, the examples I've discussed. With Gödel we had this, and then everything went well until the end. With Wiles, we had the beginning, and then there was a problem, and he had to revise the proof, and eventually he got here anyway. Now we have like the example where it starts here, but then there are these serious problems that eventually the prover gives up on the proof. So these were the 3 examples we had so far. They're all like covered by my chart, right? So you might think, great, right? So you can explain, you can narrate every single instance of proofs and how they're received by the mathematical community. No, you see in a minute. But before that, here's what happened. So here, this is what Terry Tao said about Nelson's proof. Basically, he's saying that Nelson was a very cooperative prover. He had produced a proof, well, which turned out a flawed one, which was very detailed, very easy to understand, and then made his job as a skeptic much easier. He said, Nelson's proof was relatively easy to understand, in part because he took the trouble to write out a short outline which makes clear, well, I guess this was on the blog, right? So he was probably typing real quick, the general strategy of proof while omitting most of the technical details. So he's just saying, compliments, kudos to Nelson because he produced an argument that was very detailed, so it was easy for me to find the problem with it. And now, the final example I have, which is where things seem to be breaking down, right? The nice, harmonious interaction between prover and skeptic. This is an example where things haven't gone well for more than 10 years now. So this is about the ABC conjecture. And this is, a very simple, probably not entirely accurate, but I think good enough for the present purposes, formulation of the ABC conjecture. For 3 positive integers, a, b, and c, that are relatively prime and satisfy this equation, the product of the distinct prime factors of a, b, c is usually not much smaller than c. Of course, this is like a colloquial way of unpacking it. The technical formulation, if you want to know more, you ask Tim. He's a mathematician, not me. But anyway, the point is that this is a very important conjecture. It entails a lot of other things. So if we prove this, there's a lot of other very important results that we get for free, as it were. And in 2012, Shinichi Mochizuki, who's a very distinguished mathematician, had been doing great work for many years, he announced that he had a proof of the ABC conjecture. So again, big commotion in the mathematical community. But the proof is based on a framework that he had been developing in isolation for more than 10 years, which he calls inter-universal Teichmüller theory. And what happens? Nobody understands this proof, right? So, and this is a proof in limbo, and it has been in limbo, as it were, well, although there was some reason about it, but for a long time, people didn't know if it was correct or not. Because on the one hand, he maintained that it was correct. Some of his colleagues also said, oh, we went through the details, it's correct. But by and large, other people from the mathematical community, they couldn't understand because it was based on a theory that was just too unusual. So here there is a mathematician, Emerton, who said the following: no expert who claims to understand the argument has succeeded in explaining them, the arguments, has succeeded in explaining them to any of the very many experts who remain mystified. Right? So by and large, the community didn't know what to make of it. In 18, two mathematicians, including Peter Scholze, who's also very respected mathematician, Fields medalist, etc., and with a colleague, Jakob Stex, they claim to have found a mistake in the proof. They went to Japan to talk to Mochizuki, but Mochizuki remained unconvinced. He and the people working with him, they still say, no, my proof is correct. And I was just talking to Tim over lunch, what's the current status? And it seems that the current status is that by and large people in the relevant community are siding with Peter Scholze. They're thinking, well, if he found this mistake, given his stature as a mathematician, he probably has a point there. But it's not, there's still this controversy, right? So this is where the prover-skeptic collaboration kind of breaks down. And the question now is Mochizuki not being a sufficiently cooperative prover? Or, as Mochizuki and his entourage think, they think that it's the mathematical community who's not being a sufficiently cooperative skeptic because they're not taking the trouble of learning this difficult theory that he developed in order to really be able to understand the proof. So that's the story where there's like mutual accusations or you're not being cooperative enough. Just to wrap up, right? So as I said, the overall slogan of my whole work on this is mathematical proof is at once oral and written, a phrase that I borrow from Réveillon-Netz. I claim that deduction has dialogical roots, historical roots, conceptual roots, and these roots are still present in theories and in practices of deduction. But also that these practices display non-dialogical features, monologue, it can involve writing and special notations, so that's why it's at once oral and written. And the dialogical account that I presented here highlights this inherent social nature of the production of mathematical knowledge. Here again, one can think of Lakatos, who was somebody who was also highlighting this idea that you needed the dialectic between proofs and refutations. And my claim is that mathematical communities are also composed of real-life prover and skeptics who are constantly collaborating with each other in an adversarial way, as it were, trying to find problems with each other's proofs, but they're really collaborating to produce new proofs and new concepts. And that's it. Thank you.